So we're going to continue our discussion today talking about advanced Java completable future features. And now we're going to show how to apply completion stage methods in a bit more comprehensive tutorial. So up to this point, we've been talking about each of the different features in isolation, kind of showing small examples. And now we're going to put them all together and show how to apply these methods in context. So this particular example comes from my EX8 folder, which is part of my GitHub repository as always. And this particular test is called test fraction multiplications 1, which might imply, as is the case, that there's a test fraction multiplications 2 test as well, but we won't have a chance to talk about that right now. So what this test does is it uses a Java sequential stream generate factor method. This will generate an infinitely large stream. And what we're going to do here is we're going to call a lambda expression that will invoke the make big fraction factory method. We'll talk about that in a second. And what that's going to do is it's going to generate an unbounded number of large, random, and unreduced big fractions. And then we're going to use the limit method, which is an intermediate operation that will essentially stop the processing after a certain number of items have been generated. In this case, S max fractions number of them. So we're generating, ultimately by using these two methods together, a bounded number of large, random, and unreduced fractions. Here's what the make big fraction method looks like. It's a factor method that creates a large and random big fraction. As you can see here, it takes a random number and a Boolean to indicate whether the number should be reduced or not. And the random number generator is then used in a couple of interesting ways. So first, we're going to go ahead and generate a numerator. And the numerator is going to be a big integer that will be randomly distributed over the range 0 to 2 to the 150,000th minus 1. So I think you'll agree with me that's a very, very large number, or potentially a very large number, depending on how the range is distributed. So we got an absolutely gigantic numerator. And then we go ahead and make a denominator by taking the numerator and dividing it by a random number between 1 to 10. So that, of course, will be a smaller number. So that is our denominator. And then we use the value of factor method on big fraction to combine the numerator and denominator together to make a big fraction. And we pass in the reduced flag, which indicates whether or not we want to be reducing this or not. In this particular case, as you'll see, we pass in a false flag to here, so that will not be reduced. Okay, so now let's say, just for sake of argument, that S max fractions is 50. So what we're going to do there is generate 50 random large big fractions. And then what we're going to do is we're going to connect that stream of large random big fractions with the map intermediate operation. Remember, map is going to apply a function to every element in the stream. So let's just say, for sake of argument, we've got 50 elements coming through the stream, and we're going to apply the reduce and multiply fraction function to it. Here is what the reduce and multiply fraction function looks like. It's a function that maps big fraction to completable future to big fraction. And you can see here that what it does is it uses the completable future supply async factor method to go ahead and asynchronously reduce the big fraction. So you can see what it does is it takes the unreduced frac, which is basically the big fraction that's passed to the function as a parameter, and it goes ahead and it calls reduce on that, and it does that in a background thread because it passes that supplier lambda to supply async. So that will arrange to run that supplier lambda in some thread in the background in the common fork join pool. And what will happen when that computation, when that supplier lambda gets run, is it'll go ahead and reduce the big fraction. Okay, so far so good. Then what we're going to do here, just to show a couple of different things, is we're going to use the then compose method. And then compose is a completion stage method. And of course, what that means is it's going to be invoked after the completable future return from supply async triggers. It will trigger, of course, after the big fraction has been reduced. So after the big fraction has been reduced, then compose will be invoked because it's a completion stage method. And the action it's going to be passed is going to take the reduced fraction, which was what was reduced in the background by big fraction reduce, and it's going to go ahead and multiply that reduced fraction by some constant, where the constant is just some big fraction that we've defined somewhere else. And it's going to do that using supply async. So you'll notice that we're going to then do an asynchronous multiplication in a background thread by using supply async again. So we use supply async up here to do the original reduction, and now we're using supply async down below. Now remember that supply async returns a completable future. And we don't want to have a completable future to a completable future, and that's why we use the then compose method. So then compose, as we've seen before, acts like flat map to ensure there's just one level of completable future nesting. If we used then apply, we'd have a completable future to a completable future, which would be somewhat unwieldy. There's an alternative way to do this, which is what's shown in test fraction multiplications 2, that alternative method that's part of that EX8 example in my GitHub repository. And this way we can get the asynchronous processing that we had here, but the difference is we don't have to call supply async a second time. So remember over here we're calling supply async a second time, and then we have to use then compose to make sure we don't end up with nested completable future results. But another way to get the same thing done is to use then apply async, where we give it an action to run, which in this case is going to multiply the reduced fraction with the S big fraction, and then apply async is going to end up doing that in another thread in the thread pool, but we don't have to call supply async directly. So for my money, I would prefer the then apply async model here instead of using then compose and supply async. And if you go back and watch the completion stage videos from last time when we talked about completion stage videos, you'll see that there's some discussions about then compose and supply async being replaced with then apply async, which is a preferable way to go. Keep this in mind because when you do your programming assignment, assignment number 3, you will end up using then apply async, and you'll also end up, I believe, using then compose async as well, but I don't want to spoil the surprise. So you'll have to go watch the video where I walk through the skeletons in some detail talking about what you have to do. Okay, so remember, map will apply a function, and then it'll basically return a stream of whatever the function created, whatever types the function created. And there's always a one-to-one mapping between the number of elements that come in to the map intermediate operation and the number of elements that come out of the map intermediate operation. So what's happening here is we're mapping a stream of random large big fractions that are unreduced into a stream of completable futures to basically big fractions that will be reduced and multiplied by the time everything gets done. So that's what's coming out of map. So now we're going to have a stream of completable futures to pending operations that are going to be reducing and multiplying asynchronously in threads from the common fork join pool. So that's what comes out of map. Now what we're going to do is we're going to go ahead and collect the results together. And this is just the super coolest thing ever. This is going to use something called futures collector. I will talk about futures collector shortly. You will actually get a chance to use a variant of futures collector in your programming assignment number 3. And futures collector is really the bee's knees or the cat's meow or whatever you want to call it. And what it does is futures collector is a collector that's going to collect a stream of completable futures to elements of type T, because it's all generic, of course. And it will return a single completable future to a list of big fractions. And that completable future that's returned from collect will be triggered if and only if all the asynchronous computations that are running have finished. And we'll see how that works. And when that happens, once that one and only future triggers, then we're going to have the then except method called, and it'll go ahead and sort and print the list. So we'll see how that gets done as well. Here's the sort and print list method. We will come back, by the way, and talk about how the futures collector works in just a second. But first, I'm going to show you how to do the sort and print list. This is also super duper cool. It's a variant of something else you've seen before, just using it in this context. So what we're going to do is we're going to take a list of big fractions. This list now contains the contents of the reduced big fractions because they've all been reduced and multiplied at that point. And what we're then going to do is we're going to kick off two sort operations, one of which is going to use quicksort and one of which is going to use merge sort. And it's going to go ahead and quicksort and merge sort those lists in parallel because you can see that we use supply sync twice. And we're going to store the completable future that comes back from supply sync in a local variable, quicksort f and merge sort f. And then what we're going to do is we're going to use the except either completion stage method, which if you recall what it does is it takes a completable future that is what except either is called on and a second completable future as the first parameter. And whichever one of those two methods, or sorry, those two completable futures finishes first, we're going to take the results that come back from that, and then we're going to go ahead and apply this particular action. And this particular action is going to take the sorted list that came back from either quicksort or merge sort, whichever one it was, and then we're going to go ahead and iterate through that sorted list using the for each method, and we're going to display the fraction as a mixed string, each of the fractions in sorted order in a mixed string. Now here's an interesting little bit of trivia. If the future either, whichever one finishes first, quicksort future or merge sort future, whichever one of those finishes first, if they finish before except either is called, then that will be where that thread that calls except either will be the one where the action is run. In contrast, if except either is called before the completable futures are done, or the first one is done, then the action will run in the thread where the previous stage ran. So this is a really, really, really super subtle point. Doesn't really matter for the most part, but it's just an interesting piece of trivia. Also, keep in mind that except either does not cancel the second future after the first one completes. So after the first future completes, then the second future is not canceled, it's just ignored. And that's because there could be some other part of the code that wants the results of that completable future, so it doesn't go ahead and unilaterally cancel it. So that's the end of an overview, kind of walking through how you can apply these advanced completion stage methods to various good effects. And we use that particular example to demonstrate how it works. So I recommend you take a look at the code that's in that particular example and feel free to play around with it. We're going to look at some other nuances of this here in a minute, but this should give you a good starting point. And it also teaches you a bit about some of the things you'll need to know to implement the next programming assignment.